In the early 2000s, web servers hit a hard mathematical ceiling known as the C10K problem, the inability to handle 10,000 concurrent connections. To understand why systems failed at this scale, we have to look at the industry standard at the time, pre-2.4 versions of Apache HTTPD. This architecture relied heavily on synchronous communication primitives. This is a blocking operation. For every request, the server locks a unique thread with dedicated memory. Since network speeds are slower than CPUs, threads sit idle waiting for I/O. When connections surge, memory consumption spikes exponentially, inevitably causing an out-of-memory crash. The traditional workaround was pure brute force. Engineers deployed massive reverse proxies with load balancing across a high number of physical machines, simply to aggregate enough total RAM to keep the threads alive. NGINX was created as a direct, purpose-built response to this specific memory exhaustion crisis. Achieving true scalability required abandoning the thread-per-connection model entirely in favor of an asynchronous architecture. This diagram outlines NGINX's core architectural pivot. It adopts an event-based model that distinctly separates a single master process from multiple worker processes. The master process serves a strictly administrative role. Its primary purpose is to read the configuration file and validate its syntax. Beyond parsing configurations, the master manages the entire lifecycle of the child processes. It handles starting, stopping, and maintaining the workers as they execute. Because of this strict separation of duties, the master process can reconfigure the server on the fly without ever interrupting active client services. The actual engines of the system are the worker processes, which are built to handle the heavy lifting of network traffic. A single worker process operates with immense capacity. It can autonomously manage many thousands of concurrent connections and process thousands of requests per second. To optimize this architecture, there's a critical hardware constraint. The number of active worker processes should be matched exactly to the number of available physical CPU cores. Configuring a number of workers that exceeds the available CPU cores forces the operating system into expensive context switching. The CPU wastes processing cycles swapping processes in and out of memory, destroying overall efficiency. NGINX's strict master-worker split achieves an incredibly conservative memory footprint by limiting active operating system processes to match the physical hardware. This brings up a technical paradox. How exactly does a single operating system process juggle tens of thousands of requests without spawning new threads to handle them? The answer lies in OS-dependent mechanisms, specifically non-blocking event loops. NGINX relies heavily on system calls like epoll or keyvent for multiplexing. Under this multiplexing mechanic, workers do not wait on individual connections. Instead, they accept all new requests from a massive shared listen socket. Unlike the earlier blocking model, NGINX allocates processing time to a connection only when a specific I/O event occurs, for example, only when data is actually ready to be read or written. Because processing power is applied only during active data transfer, central memory consumption increases very slowly and linearly as concurrent connections grow. The event-driven state machine seamlessly drops idle connections back into a dormant pool, picking them up again only when their next I/O event fires. This architecture completely eliminates the need to spawn a new process or thread for every connection. By decoupling connection volume from RAM limitations, asynchronous multiplexing definitively solved the C10K problem. With the operating system level architecture established, we can examine application layer configuration. How does a worker actually decide where to send a processed request? NGINX relies on hierarchical configuration contexts to evaluate incoming URIs. A block of directives applies to specific levels of the server. These routing rules cascade from the global HTTP block down to a server block and finally into a location block targeting specific resources. The golden rule is precision. When evaluating URIs, the server always selects the longest, most specific prefix match. Often, these matched location blocks do not serve local files directly. Instead, they use the proxy pass directive, acting as a reverse proxy. The proxy pass command routes traffic out to an upstream block, a defined group of back-end application servers waiting to process the data. This positions NGINX as a powerful load balancer, tasked with optimizing resource utilization and ensuring fault tolerance across these back-end systems. Traffic is distributed based on configured methods. The default load balancing policy is round-robin, which distributes incoming requests sequentially across the upstream group. To protect busy application servers, administrators can deploy the least connected policy, routing the next request only to the node with the fewest active connections. Alternatively, the IP hash directive uses a hash function based on the client's IP address to determine the correct backend server. The primary benefit of IP hash is session persistence. It ensures that requests from the same client are repeatedly directed to the exact same backend server. These cascading contexts and load balancing heuristics transform NGINX into an intelligent, programmable traffic director. This architectural model demands a deliberate trade-off. NGINX prioritizes massive throughput and reduced latency by pushing complex processing downstream. Modern performance baselines reflect this. While recent 2.4 versions of Apache have vastly improved their concurrency models, they still trail NGINX at extreme scales. NGINX's absolute advantage lies in its file system operations. It is demonstrably faster and more memory efficient when serving static resources directly to the client. However, because of its asynchronous nature, NGINX can be slightly slower when tasked with serving and rendering complex dynamic resources natively. Engineers resolve this trade-off by combining both technologies into an industry-standard deployment pattern, the hybrid stack. In this configuration, NGINX sits at the network edge to buffer the immense concurrent connection load. It handles all the static files instantly, shielding the rest of the network. By dropping idle connections early, NGINX passes only a filtered stream of active, dynamic requests to the Apache cluster. Apache is then freed up to use its synchronous processing power purely for generating dynamic logic, without the risk of memory exhaustion. NGINX functions as a highly reliable, asynchronous shock absorber, protecting the backend infrastructure from the volatility of external connection loads.